So, okay, so continue. Okay, so we have psi in region 1, x equals 0, equals psi in region 2 at x equals 0, right? So you have, we're connecting the two wave functions. We're connecting those bits, right? So you have this bit and you have this connection point, and we're trying to stitch them up. So if you mathematize that, right? So if you just take our expression, let me just remind you what those psi's are, right? So in region 1, we have equals c minus e to the plus kappa x. In region 2, we've already knocked out 2 terms, right? I think I call it sine. All right, and so in region 3, and to remind you, kappa. Oh, okay, so let's apply this boundary condition right here, right? So what happens if I do that? So I get c equals b, right? And then the second boundary condition is psi prime, the derivative, ddx. At region 1, x equals 0, equals psi prime of region 2 at x equals 0. BC1, this boundary condition, right? So this is BC1, and this is BC2. BC1 allows this kind of thing. It just says connect. BC2 says not only do you have to connect, but you have to connect in a way that makes their slopes match at the connection point. All right, so therefore this violates the smoothness, BC2. Anyway, so what does this say? Psi1, if I take psi1, if I take the derivative, I bring the kappa. Okay, and so, okay, so let's just do it. C kappa e to the kappa x, evaluate x equals 0, equals ka cosine of kx, evaluate x equals 0, minus kb sine kx, evaluate x equals 0. Okay, so this will be 0, this will be 1, right? And so what I get is I get c kappa equals ka. Okay, so I have one equation, 2 equations. And then what are the other boundary conditions, right? So you have BC3. Yes, folks, if you think this is tedious, this really is how it is. So this idea of solving a problem like a homework problem in 1 or 2 lines, that's not how the real world actually functions. A real calculation, you know, in the adult world takes 40, 50 pages sometimes, okay? All right, but I won't make you do that. So if you apply BC3, you do the same thing, you will see that F equals, right, so BC3, we're applying at x equals L. right? So on the left-hand side, you get f e to the minus kl, or kappa l. And on the right-hand side, you get a sine kl plus b cosine kl. All right. Bummer. It's not as pretty as we were hoping, huh? And then finally, there's a BC4, which is even a little bit messier. So the teachable moment here is you can see how real calculations are actually done. Minus kappa f e to the minus kappa l. This came from taking the derivative. And then you have a k cosine of kl minus b k. Cosine becomes a sine of kl. Okay, so this is equation 3, and this is equation 4. Now I'm boxing them, not because they're super important, but that you can see there's 4 equations and 4 unknowns, right? So you have 4 equations, the ones that I boxed, and 4 unknowns. What are the unknowns? A, C, A, B, C, and F. In principle, we can solve 4 equations and 4 unknowns. Okay, so from the first two, from this one and this one, what do we learn? Well, first of all, it says B equals C, so I can substitute B right here. So I'm using up equation 1, and this gives me B kappa equals AK. And so from the first 2 equations, from the first 2 equations, I learn that B equals K over kappa times A. And so I'm going to substitute that into here. So now I'm just going to have, okay, so sub, I don't know why I'm using this thing. Sub into the last 2 equations. Okay. And then what you get is you get something, a beauty that looks like this. And what you do in the other one, minus kappa over k. Notice this is k over kappa, this is kappa over k, right? Just to make it extra sweet. Okay, so the first, and then this, okay, so now we have 2 equations. Sub the first into the second. Okay, so let's do that. So basically, f e to the minus kappa l equals all this business. So I'm just gonna substitute that into here. That's how the substitution works, right? Sine kl plus k over kappa a cosine kl equals a cosine kl minus k over kappa a sine kl. And what can I do? Well, exactly, I can cancel out the a. When can I do that? If a is non-zero. But if a is 0, notice if a is 0, that means f must be 0. And if a and f is 0, well, if a is 0, that means b. If a is 0, it means c is 0, it means b is 0, then you get just a zero solution. So A cannot be zero, otherwise you get a trivial wave function, psi equals zero. Psi equals zero is always a solution, but it's not a solution that we're interested in. Okay, so now the rest, I'm just gonna cut a lot, right? So simplify and rearrange. Okay, some more, and then you get something that looks like this. 2 cosine KL equals K over kappa minus kappa over K sine KL, or 2 cotangent of KL, not or, let me say. Or is not the right word here because it sounds like it's either or, i.e. 2 cotangent of KL equals K over kappa minus kappa over K. Okay. And then after some more algebra, which I'm not going to show to you, when the dust settles, we get, there are 2 possibilities. Either, so now I can say or, either cotangent of KL over 2 equals KL times DL squared minus KL squared taken square root, or, now I can say or, sorry, this is cotangent, not cosine, it's a cotangent. Cotangent. I'm doing very well today. I'm catching my mistakes. KL over 2 equals KL times DL quantity squared minus KL. KL squared taken square root. And I say, why don't you just cancel the L's out, right? Because I want to keep things that are dimensionless, that are unitless. K has units of 1 over meters, L has units of meters, or you could say K has dimensions of 1 over length, L has dimensions of length, and I want to keep things dimensionless. I want to express things in dimensionless terms, because you see, this is dimensionless, this is dimensionless, this is dimensionless, this is dimensionless. I like to work with dimensionless groups of parameters. That's the proper way of doing things. That's why I'm not canceling out all the L's, even though it looks like it would make things easier. Also, we recognize that we can just call KL, we can call it like X. And then I have cotangent of X over 2 equals X over, we can come up with another letter for this, like A minus X quantity squared, right? So that's almost like cotangent of X over 2 equals X over, I don't know, A squared minus X squared. Whereas if I did cancel out the L, you don't have the single X on the left and the right hand side. So it's better to work with dimensionless groups, because when you do, then you end up having the same quantity on both the left and the right hand side. That's why I'm not canceling out the L. Okay, so I'm gonna erase this because we won't need this, so I don't want to confuse you with extra variables. Okay, what do we do now? Can you solve this for KL? You can't. You cannot write a solution in closed form, like square root of 2 or 1 over pi squared. So to help ourselves, we now plot this versus KL and the right-hand side versus KL. And we can also plot this versus KL and this versus KL. So plot everything versus KL. I'm going to treat KL as a variable like X.